Hello, my name is Halen Cheney, and this is my presentation on Lab 1. Introduction, we're kind of going to go over Newton's first law, and then we're going to go over constant velocity and what that means in terms of force and acceleration, which is Newton's second law. We're going to go over the forces that are acting on our experiment, which are gravity and normal force, with friction and air resistance. And the conclusion that we got from our experiment was a relatively constant velocity, even though there are other forces acting on it to make the net force not equal to zero. So the physical principles that we went over were Newton's first law, which is an object that is in motion will stay in motion unless acted upon by another force. So I will discuss our experiment later, but we also went over Newton's second law, which is force equals mass times acceleration, and when the net force is zero, acceleration is zero, and vice versa. And the forces that acted upon the marker were gravity force, which pulls it straight down to Earth, and normal force, which fights back and pushes back on the marker. So for the experiment, we rolled a marker in a straight line in a positive x direction along a meter stick, and we took the points and put it in a tracker, and we took the points and measured the distance traveled between each point so that we could determine the velocity of the marker in that time duration. In a perfect world where there is no friction or air resistance, there is zero net force because the normal force and gravity force cancel out. But in this situation, there is slight friction and air resistance working against the positive x direction that the marker was rolling. And in the experiment, we measured the velocity, again by taking the distance traveled over a specific time. In the code here, I did not change the initial position vector, but it started at the origin, and we found the initial velocity of the ball, by taking the average velocity that was found in the experiment. So we just put the average velocity in the code, just because that's a pretty accurate, about as accurate you can get at least of an experiment. The delta t was 1 frame, which is 0.033 seconds, because that's how often it measured the position. And to find the position of the ball, we would take the initial position, or the position that it was in, and then add the velocity times delta t, which is pretty much just the position update formula. And then comparing the graphs, the one on the left is the real life graph, and the one on the right is the simulation graph. And as you can see, the position graph in real life did not go as far as the simulation because of those other factors like air resistance and friction force that are not accounted for in the simulation. And kind of the same story here, where there is a slight downward slope in the velocity in the real life simulation, or the real life situation on the left, which means there was a slight bit of negative acceleration in the x direction from air resistance and friction. But in the simulation, there's a constant velocity, because in the simulation we did not account for gravity or air resistance. A big what if is, what if we inverted it as an x-axis? And the answer is nothing would really change. We would still it would be the same magnitude of a vector, just be slightly, or the opposite direction actually. It would be in the negative x direction rather than the positive x direction.